So I put this huge thing up just to get people thinking ahead of time. I want to give you all first a sense of the applied problem, right? About human interaction, what examples where we do these experiments. I do have to say before I start, the disclaimer I have to give is I'm from Trinidad and Tobago in the Caribbean. People tell me that I have to say this because otherwise they miss the first part of my talk trying to guess where I'm from. Now you all know I have a full attention. If you want to read more about these papers, they're at our website, papers, and I have a link to my research team, time.cc Williams Research, which is basically an overview of what I put in for tenure. And this URL, time.cc join IA extended, is our mailing list. You can join that, and then you can listen in whenever we have a lab meeting or a special meeting, we announce it, and you can always pop by and listen in. We're trying to think of a global network of people involved in adaptive experiments. So here are my objectives for this talk. By the end of this talk, I want everyone to be able to have some kind of shareable message, right? You could tell someone else what is interesting in a paragraph. In a person, you could tell the person next to you. By email, you could send them a link to this talk and tell them why it's interesting, or maybe a LinkedIn or Twitter post. You want to have some kind of concrete information that comes out of this, like being able to explain how adaptive experimentation can be used in a wide range of behavior change contexts. Or you have ideas for how you could contribute to helping someone win a Nobel Prize for adaptive experimentation. I also want you all to have a clear to-do or could-do. What's one thing you could do? Before you saw this talk, you were on one trajectory. After, what are you going to do differently? Is it going to have any impact? Would it be joining a mailing list, reading a particular paper, or share these slides to someone? Or give feedback, like the world should change in some way after we had spent an hour together and more. So think about your hashtag shareable message and your to-do or could-do. You'll be quizzed at the end. Right. So this is the overview of the talk I gave yesterday. Fundamentally, what's the goal of our program? It's to coach behavior change. For example, how do we coach people to learn more effectively? Like I just did by prompting you to have like a clear shareable message or to do. How do we coach people to manage stress better? How do we coach people to exercise or eat healthier? And what's our approach to that? Our approach is that we transform everyday technology touchpoints into intelligent interventions. And I'll say what that means and how the adapcomp framework supports that and helps us win the X Prize. So there are three components to this work. The first is adaptive experimentation tools that make experimentation easier and expedited, because this gives us more effective interventions. For example, it gives us better explanations of a concept, or gives us messages that will help someone actually deal with stress better. The second theme is personalized and contextualized interventions, and the papers I present there all work by Ananya Bhattacharjee and others in my lab. And finally, adaptive experimentation to accelerate science and practice. Now, that's what the actual full talk will be on. I'm going to abbreviate the first two parts just to give you all a taste of an example or two, so you can keep that in mind. Now, the science of behavior change can help solve many human problems. Imagine if you could get the magic words to change any behavior. What are behaviors you wish you could start doing? Is it introducing yourself to people, exercising, connecting better, being less stressed? What are behaviors you wish you'd stop doing? Is it that you just don't speak up when you know you should? Is it that you keep eating 10 snacks instead of 2? Are you scrolling on Instagram or other things way too much? Nathan Laundrie, one of my PhD students, works on that. Also, behavior change in others. What behaviors you wish others would do more or less often in different contexts? And do you all see how this touches on every aspect of what we do? Change our behavior in learning, making better decisions, exercise, eating, stress, happiness. And I'll focus in the examples I'll cut how technology can help us in behavior change in both education and health. So the vision we're looking for is, by 2034, how do we have on-demand intelligent coaches that measurably help people think through many problems and change their behavior for good? What have we done so far to get to that point? From 2012 to 2024, we've earned a foundation. And this is through the adapcomp framework, which helps us get tools for designing intelligent interventions. An intelligent intervention, whether it's a text message you get sent, or an app message, or an explanation of a concept, is an intervention that changes your behavior. And it's intelligent in the sense that it tries to come up with what's the best thing to give you at this point in time. But also, true intelligence is about learning. It's constantly testing out ideas so you can learn what is going to help you. If someone tells you they built an intelligent system and it does involve learning and continuous learning, I mean, I have lots of snake oil I'd like to sell you. And to build intelligent interventions, we have to integrate multiple disciplines. So what examples of intelligent interventions we've been working on that can help towards this coaching behavior change? So what we do is we essentially take components of everyday experience and make them into adapcomps. The adapcomp framework takes a static user interface, like a text message or a website, and makes a micro lab for intelligent intervention, where we can keep testing out ideas and improving them over time. For example, text messages is one that Ananya Bhattacharjee and others have been involved in. Imagine getting a message of the day, but that's an adapcomp. And what that means is we crowdsource many ideas for those, so we keep testing them out. Use LLMs, use people's input to generate ideas and messages. And then we try and figure out which of those is best for you when. When do we emphasize, get up and go for a walk right now, you've got to do it. When you tell someone it's okay to feel kind of lazy, you can take a break for 10 minutes and come back to this later. The idea is we want to figure out, as a coach, what we're going to say to you at the right moment in time. Think of emails as well. One of my PhD students who just got a job as a faculty member has focused on emails you send people to get them to start homework early. But again, we try dozens of options, crowdsource from human beings and adapt through LLMs, and try and figure out when do they work in different contexts. But do you see how we take something as boring as email and turn that into an intelligent coach? The adapcomp lets you take the subject line, the intro message, and generate multiple versions and test out what works when. So anything you touch every day could be an intelligent intervention. Of course, you can imagine explanations on a website. Sadly, I will be embarrassed to say, my website is not intelligent intervention. You get the same thing that's been there for 6 months, and you should shame me for it until I fix that problem. When you show up on my website, you should have an adapcomp. It should randomize you to different explanations. It should let you say, Joseph, this was garbage. Here's a better explanation. And it should be A/B testing that to figure out which explanations are better on average and what works for you at this moment in time. Does that make sense? How you want to make that piece of a website an adapcomp? We have actually done a better job in other people's websites. In 2013, when I was at Berkeley and Stanford, we actually ran experiments at Khan Academy, where we'd actually test out different explanations of concepts, different messages to motivate students to work harder. And increasingly now we're doing it in LLMs. I want to say for all the good LLMs are doing, aren't you all a bit frustrated? In an LLM, it's so easy to generate alternative versions. Anything in conversation, they can make dozens of versions of, and they don't do it. Why are they not A/B testing LLM components? When you go to ChatGPT and it gives you an answer, it could test 10 versions of that answer to figure out what's going to actually help you. They have recently introduced some nice features, but those are just first steps. They could be A/B testing 200 times more than that. So does this give you all a sense of how everything you touch in the world could be an adapcomp? It could be an intelligent intervention that tests out different versions and changes over time. Who's sold on that? Who understands what I'm saying? Okay. You have to be sold once you understand.
So I wrote this in the chat, but I'm unclear about how you're going to have sufficient statistical power for these. These are small text changes. The impact on, let's say, click-through rate is going to be very small. So you're going to need to send the email to tens of thousands of people.
Mm-hmm. Yes.
How does that work? Like, I understand if you're a portal and you've got all the users, but for everybody else out there, you're saying send an email. This is not a major spam to 100,000 users. You're not going to have statistical power.
That's a great point. So I'll reiterate the question. So if we want to make this approach ubiquitous, how can we make this possible? Because you won't have enough data, right, to do this. So I'll say two things. One is that we take this approach in settings like education and mental health, where we've actually built collaborations to do this at scale. So if you do have 500, 1,000, even 200 people, you can apply this approach, right? But the second thing I would say is this. This is exactly what we're doing next. So one of our papers, you can read on our website, it's called A/B Scribe by Mohi Reza. That's about qualitative A/B testing. What if you actually could take the best features of A/B testing and use them qualitatively? Even if I'm only sending an email to one person, how can I actually gather feedback to understand the different options? It's also connected to something I would call a thought A/B experiment. Tell me something. When you write an email, could it actually make sense to use our A/B Scribe tool to make different versions and then try and think through in your head how these would come together? So you get no data. It's all in your head. But the process of A/B testing will make you lay out alternatives and think about the impact. And that's actually what I want to do a lot more work in. Yes.
I guess conceptually, A/B testing is this statistical rather than qualitative exercise, at least the formal definition. I wonder if there's a name clash thing where maybe that's not the right name for.
That is exactly on point. Okay. The word A/B testing means something to everyone. I'm trying to come and tell you all, this thing here that you call a chair, it's now going to be something we fly on. Okay, so that's a great point. So here's the exercise, everyone. Here's how you can contribute, Obama. Here's how you can contribute to a crowdsourced Nobel, okay? Come up with a different word for those A/B tests that actually are qualitative. Qualitative A/B comparisons, super A/B comparisons. That's your exercise for homework, okay? And then I can take it and you can charge me if I ever make money off of it. For now, I'm going to call them a qualitative A/B comparison. All right, so now in terms of intelligent interventions, right? Here's a process. And I want to get you all thinking, how could this process work even if you do not have quantitative data? So here are the elements, right? You take an adapcomp, like one of those messages we just saw, and you now think, part one, how do I make it easy to generate options? For example, if I'm writing an email, how do I generate alternative versions using both LLMs and crowdsourcing from human beings? And then explore that space of options. Come up with better ideas. Part two, now how do I exploit the evaluation of these options? What might be more or less promising? But also, how do I exploit execution? What do I mean by execution? I mean actually using adaptive experiments to give people what looks better. To integrate reinforced learning and human judgment. So a very concrete example would be, let's say we have two versions of an email, right? I can ask you, what's the probability email A is better than email B? If you tell me, actually, can I ask you in the red, what's the probability that, let me show you an actual email? Okay, just make it up. There are two emails hidden in my hands. What's the probability A is better than B?
I mean, what are the, like, where are the emails coming?
You know nothing else. 50-50, right? Well, look at that. You think there's a 50% chance. So why don't we assign with 50% probability? What do we have? Classic A/B testing. Now, she unfortunately knows more than you. And she says there's a 70% chance A is better than B. So what should we do? Assign that to 70% of people. Does that make sense? Well, pick on because I know him. It's like, no, if there's a 70% chance, you should give everyone it 100% in time. That's actually what we all do. We are arrogant, right? When I write an email, I send an email 100% in time. I'm saying, I'm 100% sure that is the best email I could have sent you. I did no randomization. So you see, we live in a terrible world. Like Daniel Kahneman said, we're binary creatures living in a probabilistic world. We either give someone something 100% time, like I'm today giving you one version of this presentation 100% in time, or we give it to them 50-50. We don't have these in-betweens. An adaptive A/B experiment says, let's randomize with weighted randomization proportional to our belief. So if you think, like she does, there's a 70% chance A is better than B, why don't you give it to 70% of people and give it to 30% of people? Then you get more data. And this data can be quantitative or it can be qualitative as well. You might just see if people react negatively and say, 70-30 is too high. I think it's actually like 20-80. So the idea here is let's kind of start rethinking the world to not just give 100 or versus 0, there's one best thing, and not just give 50-50, which is A/B testing when we have no idea. Let's actually give things proportional to the probability we think that there's going to have the best outcome. Does that make sense, everyone? At least conceptually, do you all get the idea that we could actually start assigning items or actions, emails, texts, things we say, proportionally probability we think that they're the best, where best has to be defined.
How do you decide the complexity of the model that you're using to weigh your different versions against? Like, for example, with the Khan Academy example, like which LLM response is the best one to elicit a particular action? I presume you have to build some kind of probabilistic model in the background for your estimate of the beliefs of the student. But there are many ways of doing that and many different ways to plan subsequent actions. And I guess, is that something that happens real time, or is that something that happens once before and then you implement a system that just runs? Or and what's the process of even figuring out what are the relevant components of your model?
Excellent questions. And I have the answer you can always answer in anything that's worth answering. 2 words. It depends. Those are fantastic questions. Those are questions we're going to spend the next 25 years working on. What is the model you're using to set those probabilities? I will give you one model today for a 2-arm case, A and B, binary outcomes, and I will show you that that model actually isn't even good enough. But you know what? Person next you might say, I want to do qualitative A/B testing. And they say, I'm going to set those probabilities by a crowdsourced mixture of experts. I'm going to get the best marketing people in the world, and we're going to ask them questions about 10 emails. They're going to all give us weightings. I'm going to combine them. Then when we send it out, I'm going to send them the data of what happened and get the market people to update their beliefs. That's an alternative method. I don't know of any papers that have done that. I'm sure 5 have, but 5 is basically none. We need a lot more work on getting human beings to set those probabilities. But I will give you examples of how we've done that using statistical models. Again, I want to say, that's good, that's fine, right? But I think we can do a lot more innovative, interesting work. And most importantly, like I said, how do we give these techniques to 8 billion people? 8 billion people are not going to run A/B tests. I love them. I'll run them. You will too. 8 billion people will send emails and text messages. They may, with the right tools that we built, randomize them a bit. Yeah.
So I want to make sure I'm like understanding your intention.
Yes.
So
what's my intention so far?
We think about statistics and A/B testing formally, but like in reality, we just write one email.
Yes.
And so you're suggesting that like we should explore this in-between space where we don't necessarily have formal statistical power, but we have all these other signals about like how did the person reply to this email, or how did you feel when you sent A versus B, and like all these other proxies that might qualitatively give you the answer about like what you think is the best to send. But like in reality, like we're just like sending one email. And so like you're trying to push us to think like this kind of.
I have never said it so well myself. Good thing we're recording. What's your intention today, Joseph? It is to get us to rethink the way we're making decisions, to bring some elements of A/B testing together, to help us think about the signals we get about what might be better or worse, and help us to start to actually randomize, right? With weighted randomization or something where we don't just have 50-50 or 0-100. We have something in between. And I think anything that moves us towards that is progress. Anything that makes me realize that when I send an email to someone, it's worth having 2 versions. Even if I don't send it, I build the habit of A/B testing, of qualitative A/B testing, is progress. Why? Because we're introducing a problem to solve a problem. Just like the person, sorry, I'm calling you out by what you're wearing, in the white Stanford hoodie said. Just as they said, how do you choose those probabilities? Good. Now you have a problem to solve. The fact that you're worrying about that is going to give me a lot of confidence. I will say what we have done, which I think is really good and can be a lot better, and is a big research program, is work on those models that are quantitative. To use Bayesian methods, and Sang Truong is working with us on this, to use basically ways of taking A/B testing data from a quantitative perspective and estimating what are those probabilities. We've done that. But I think that that's not enough. That will get you a Nobel Prize, say, in, let's say, chemistry, economics, or something, but it won't actually help those other billions of people who just want to make better decisions. That's where the qualitative work will help, the crowdsourced approaches. And here's one way of saying it. Our models basically tell you what that probability is. And I'll give you an example sooner rather than later, I hope. But let's say you have, do I have a good example? 1 second. Okay. Let's say this is an experiment, right? And I'll tell you what it's about just now. This is an advertisement. Go and check these slides out and read it. We have 80 papers, and I know you're not supposed to do this, but I tried to put a bunch of them onto a slide. So check out A/B Scribe, right, which I'm going to walk you through now. I'm going to tell you an example of an experiment, Eustress, and then I'm going to explain how you could use that for quantitative estimates, but how I think we could actually do qualitative instead. And this paper also is about general explanations. You would crowdsource explanations of people, and then do these adaptive A/B tests to figure out which ones are helpful. If I haven't got your question, don't hesitate, just type it into the CC Williams talk. I'll have that open on my phone here. All right, so what is A/B Scribe doing here? Can people tell from this graphic? This is a tool that the adapcomp framework enables. imagine you're writing an email, right? For example, email to tell students, well, you've got a test coming up. But you know what? Stress can actually help you perform better. It may not actually hurt your performance. So what do we do is, let's actually select pieces of this email and make them an adapcomp. So that thing in green, that's an adapcomp. That's an A/B test. This other one, that's also an adapcomp. So you define now, what are the things you're going to experiment with? Right? Now, you can use an LLM in this setting, where you could actually call the LLM and say, give me a different version of this message about stress that will work well for someone who's very scientific. Give me a version that will actually work well for someone who believes, someone who does yoga all the time, okay? I do yoga, nothing against it, okay? Give me different versions and let's experiment. So then the A/B scribe is then you choose a piece and make an adapcomp to A/B test. And then you generate versions with LLM. But then this is the thought A/B test I'm talking about. Because you can then actually look at these versions and toggle back and forth between them for this part. You have another adapcomp below, and you think, how do these things come together? So I might use this when I'm writing email to and think, which of these combinations would work if I'm trying to say, don't worry before your big presentation, stress can actually help you. But then I use the same tree of options when I'm writing to someone else. Does that make sense to everyone how basically you're doing this thought A/B test or thought A/B comparison by having the adapcomps that define options, thinking through different versions, getting LLM to help you, and then traversing them. Does that make sense to everyone? Okay. So now this, I think, is the future. And I'm not sad when he got a job. I'm happy for him. But I feel like we had so much more to do on this. Okay. And any one of you can publish really high quality papers in this area by just building on this. So what's an example of using this? What does it get you? Well, here's this paper. This is a paper of Mohi Reza's and Angela Zavaleta from CHI 2023. We talked about magic words, right? And you probably thought that's BS. But tell me something. What could I say to you in 3 minutes if you're a first-year programming student that will increase your performance on a test by 4%? I don't even know if the answer to the test question I could tell you in 3 minutes would help you, okay? You'd forget it. But here's what we did. We took research in psychology by actually people in your psych department at Stanford. And I'm sorry, I forgot your name. And we then mapped this to our setting. We came up with 6 different elements of this in the adapcomp. We varied the text, we showed people the instructions, a video of me saying it or not. Link to the paper for those who are scientific. Ask them to explain what they thought they'd learn. Had them write a note to themselves. And the core message that we traversed in many ways was, when you're stressed, it can actually help you perform better on a test. It doesn't have to hurt you. That message on its own, well, you'll think that it did. That message on its own is the control group, okay? So the average grade there was 76%. But when we went through many other options, when we elaborated on it, like helping them think, well, when you're stressed, you might think it would distract you, but it can actually help you put more resources in, make you pay more attention. So during the exam, when you're stressed, you don't have to worry about it. It might actually be helping you perform better. So those examples are what we did, right? Make sense to everyone? Now, here's the payoff. When you explore these options, you will find options that actually will boost grades. So here's what you see on average, about 80% compared to 75. Well, I think that's 80% compared to 76.2 or something. That 3-minute message, which I'm not even sure they read carefully, boosted grades by 4% from a B to an A minus. So do you all see some of the payoff you get when you actually run these many experiments? I think we ran like 6 different experiments in a couple of months, whereas traditional research might take, a couple of years to run that many experiments with 200 people. That's the payoff. Now, let's ask a question. Should we just start giving this message to everyone? Every class at Stanford, at Berkeley, at everywhere? What's the probability that this particular message will work in your population and will be the best thing you could do? It's not 100, right? Nothing in life is 100. So you could imagine that if you took this message, you would then actually take A/B Scribe and use the LLM to come up with different versions, use crowdsourcing, come up with many versions, and then think to yourself, well, what's the probability it's going to work for people in my setting? Does that make sense to everyone? And you could randomize them that way, qualitatively or quantitatively, and get more data. Now, let me give one point to circle back. we have data here, right? Like I could look at this data and Sang or me or Tong Li and Fred Houchinson, my stats PhD students, they could calculate for you under some prior assumptions what the probability is that this will replicate in a particular setting. And that might be like, let's say 80% or 90%, okay? There's a 9% chance that this message is better for everyone. But here's an interesting idea. What if instead of just using the statistical model and just mapping it over, we were to say, what if we actually give that data to someone? For example, if someone is teaching a class, let's say we give that data to them and said, here's what the results showed from this class. Here's what the class was like. And then you could say, well, that's helpful. My best judgment, wrong as it may be, is that there's a 76% chance that this is the best message I can show my students. So do you all see now how we take quantitative data and we don't just blindly compute the probabilities based on a particular model. We then give that data to someone. We might get our model probabilities, but we get a human judgment as well. Now then we can combine a human judgment who's looked at the data with actually the particular beta Bernoulli or whatever model we used. Does it make sense to everyone?
I guess thinking about things possibly formally, it sounds very subjective. So is that a good way to maybe? I don't know how you think about this in terms of technical tools, but that may be a good way to think about how to connect to your formal.
When you say that, do you mean is it? It sounds subjective. Yes.
No. I don't mean this. I also specifically don't mean this pejoratively in any way. There's a sort of framing of the Bayesian way of thinking that's about sort of individual estimates of probabilities, and that sort of drives some of the decision making. I guess the framing I'm hearing from you sounds like it would fit somewhat well.
I think so, yes. But I'll say two things. I almost never have one belief, okay? I have a Bayesian combination of beliefs, okay? We can do this statistical model. And you might say, or let's say, okay, she might say, in my class, we're doing straight up statistics. I will not enter my beliefs in here, compute the probability based on the past experiment. And we can do that for her. But then you might say, well, I want to see her model on this data, but I'm going to add my own opinion. But then, person in the yellow and green shirt might say, I'm going to do what they did, but I'm going to crowdsource ideas from students themselves. So the idea is these are all tools in your toolkit that you could do. And even though, to be totally honest, what I'm pushing on right now is the more formalized statistical version, because that's what we've done more of. And to be honest, it's hard to convince my stats PhD students to do these kind of things. A human construction student is much more open. That's what I'm pushing on to help Susan Athey or Alan Asperu get their Nobel Prize, okay? But I think what will help more people is actually these more subjective methods. Again, what I love about math? I love pure math. It's beautiful. But tell me something. How many Fields medalists have helped people be healthy and exercise more? The really exciting part is taking math and bringing it to human interaction, right? Designing experiences, interventions to combine math. And that's where you have to start to do what they said Jeff had. What Jeff Hinton won the Nobel Prize. One of the students said, Jeff had high dimensional intuition. So here's a lovely anecdote. You come into grad school, Jeff would say, so do you want to work on things that are beautiful mathematically, great to prove, easy paper to publish, but may or may not relate to the real world? Or do you want to work on things that are messy, confusing, hard to formalize, but really help people solve problems? And the student said, but you'd always know which one you thought you should move towards. Because you had this high dimensional intuition. We may not all have it, but we at least need to try to take mathematical concepts and combine them with human behavior. Such as by crowdsourcing opinions from people. That's a well-defined process. Everyone here gives me a probability and I weight it. I can reproduce it, I can change it, I can evaluate it. And to be honest, remember, what are we doing every day? When you saw me outside, you just said what was on your mind. You were not being formal about that at all. You were being a human being. That's life. Let's make you slightly more of a formal reasoner by using things like A/B scribe and adaptive A/B testing.
So the general framing makes sense. Do you mind?
Yeah, please.
I'm doing this in case people want to skim. Yeah.
Okay. I guess people are notoriously bad at being, quantifying probabilities in any kind of meaningful way.
Yes.
I'm thinking of the premise of this class where we actually are engaging specifically with human feedback, but trying to do things that we think are low effort for people. I wonder how important it is that the signal is probability, given that I don't trust probabilities that mean anything.
That's a great question.
Versus other like perfect signals or other kinds of like lower difficulty.
Yeah, I think those are great empirical questions. Like those are good hypotheses, right, about how to pursue. I think those sound really interesting to pursue and analyze. Ronnie, I see you got some great questions in here. If someone could also put Ronnie questions into this talk. Okay, I'll come back to them a bit. We have shown cases where actually, oh yes, okay. I'll show you a case where deviating from uniform random can increase power. I think people are getting a sense of what a quantitative adaptive A/B test is, right? Let me let you all just read that for 30 seconds while I write an answer. So you all can read that, that's your homework, and see if that makes sense to you. Okay. So let me move on for a second. Here's the formulation, okay, of A/B testing. This is what more people think formally. Let me just lay it all out. So this is what's called a multi-arm bandit algorithm. It's the most fundamental form of reinforcement learning. And you can think of this as randomized probability matching. So what I said to you before about what's the probability that A is better than B, and you give intuitions 70-30. Thompson sampling basically claims to sample those probabilities. It's also called posterior sampling. Now I want to focus on the most simple form of this because I think everyone thinks we've got this and we have not got this right. Think of a beta-Bernoulli Bayesian model. So you've got two arms. For example, explanation A versus B. And what's your reward? Someone says, 1, I like the explanation, or 0, I don't. Someone clicks on your paper after seeing the explanation, or 0, they don't. Someone buys a product after explaining what it's about, or 0, they don't. So you have a set of actions, right? You have a reward or outcome, which is 1, 0. And you have a policy, or a policy learning algorithm, like Thompson sampling, which would assign 35%, 65%. What's the posterior probability? This is actually the best option. And so this setting actually is really nice and simple. Basically, you put a beta distribution on the probability that someone's going to say, yes, I like this. So you have a beta distribution for arm A and a beta distribution for arm B. And here's a nice prior. Let's do beta 1 and 1. What is beta 1 and 1? In the gray? What is the beta 1 1 distribution? If I have a beta 1 1 distribution, it's like I saw 1 success, 1 failure so far. What is the probability of someone saying they like an explanation? It's uniform. So beta 1 1 is uniform distribution. It's saying, I see no data so far, so there might be a 20% chance people will thumbs up this explanation, or 40% or 80%, they're all equally likely. So you have a beta distribution on arm 1 and a beta on arm 2. But now, this is Bayesian inference, and it's a conjugate. So what's beautiful about this is how simple it is and how interpretable it is. Now, the reward is a Bernoulli, right? Drawn with the parameter from that beta distribution. So let's be very concrete. Beta 1 1, beta 1 1 for the two arms. Let's say that we gave 5 people arm 1, and 3 of them said, hey, that was great, and 2 said I didn't like it. Now, what's our beta distribution? Our beta distribution is now beta 1 plus 3, comma, beta 1 plus 2. So now we have beta with 1 plus 3, 4 successes, and 1 plus 2, 3 failures. So we don't have a uniform distribution anymore on the probability that people think it's helpful. We have one that's now skewed a bit higher. It probably looks, I'm not going to try and draw on that, I'm not good at that stuff. It probably looks a bit like this. Let's say that actually for arm 2, we gave it to 5 people and 5 of them were like, hey, this is great, and 0 said, I didn't like it. Now we have a beta of 1 plus 5, comma, 1 plus 0. So now again, we get a skew, right? Where now it's like, I think the probably people liking that is high. But we're still pretty uncertain, right? It could actually be that there's only a 0.1 probability people will like this thing. It's just that we got a sample that biased us. Now, of course, if you had beta of 6, if you have beta of 6 and 1 versus beta of 60 and 10, then you would get a much more peak on the probability of it being high. Does that make sense to everyone? Because now you have more observations. You have the same mean. I think, could someone do the math quickly? 60 and 10, right? What's the mean of that distribution? You can use your calculator, you're allowed. What's the mean of a distribution where it's beta 60 and 10 or beta 6 and 1? What's the mean of that?
I agree they're the same. The variance should be smaller.
Exactly. So I think the mean should be like 60 over 70, right? 6 over 7. So the mean is 6 over 7. So it's kind of saying, my best guess is that the probability of someone saying, I like this thing is 6 over 7. But now in the beta, like you said, beta 6 and 1 is going to be like this, but beta 60 and 10 will be like really peaked. So you're a lot more confident. So does that give everyone a sense of at least how you could use a beta distribution to represent for arm A and arm B, the probability that people will think it's helpful? And what's really nice is how intuitive this is. Every sample you get is a success or failure. So you can just update the beta parameters. Now, this example is lovely because it's super simple. Everyone can see it and understand it. And so it's a great test ground for all these algorithms. It's also a great test ground for this qualitative kind of work. Now, does anyone here know what Thompson sampling does to basically get an estimate of the probability that A is better than B? Let's pretend you have beta 6 and 1 for arm A, and you have beta 3 and 3 for arm B. Well, what Thompson sampling would do is it would sample, draw from beta 1, 6 and 1, you get 0.5. Draw from beta 3 and 3, you get 0.4. And then assign the arm that has the highest expected reward. Well, if your beta from arm A, 6 and 1, is 0.5, then you're expecting that you'll have a 0.5 chance people thumbs it up. But if your beta from arm B is 3 and 3, and then you get 0.4, then there's only a 0.4 chance people are going to thumbs it up. So what gives you highest reward? Arm A. So Thompson sampling will pull arm A. Does that make sense to everyone? You have the beta distribution, 6 and 1, 3 and 3. You sample from each, and you can choose the arm that gives the highest reward under those parameters. And if you want to know the probability empirically, just do it 10,000 times, right? Draw, and you get 0.5 and 0.4, arm 1, arm A. Then you get 0.6 and 0.3, arm A. Then you get 0.2 and 0.8, arm B. So you can just get 10,000 samples, and you can actually compute, well, what's the probability arm A is better than arm B? Does that make sense to everyone? How you go from the beta distributions to what's the probability of the arm being better according to this algorithm? I may get an 80% probability of A being better than B, or 70%, and so on. Make sense to everyone? I really think we need to do 10 to 15 years of research just with this. It's super simple and it's not solved. When I say not solved, what I mean to say is the inference is actually not trivial, and I think there are a lot of mistakes people are making when they use these adaptive experiments and don't realize it. Cool. So again, everyone's clear how this works, how does sampling work here, and what's the underlying model. And so now you can imagine that if you have beta 1 and 1, you've got 50-50 assignment, right? Because there's an equal chance of these being good. You could also use manual assignment with human judgment. And now actually we see something pretty interesting, right? Suppose that she said there's a 70% chance of A being better than B. Couldn't one of us actually, back to the question about formalizing it, couldn't we then back out her 70-30 into betas? You could actually say, well, you could even ask the person, you could even ask someone, right? You could say, tell me something. She thinks it's a 70% chance A is better than B. Could you represent that as fictional successes and failures? And you might say, well, yes, I guess you'd expect something like that if I imagined I'd seen 10 observations before in A and 10 in B. And of those, I think, 8 were successes in A, 2 were failures. And in B, it was 5 were success, 5 failures. So now this is super interesting, right? Because we can actually formalize these probabilities that are so slippery. And I think there's a great Chi paper to be written simply on that. Let's understand how people could express the probability something A is better than B, and then try and map that to beta distributions and kind of help people understand which of those assumptions match what they're saying. Like, how do we actually help people formalize their beliefs about whether A is better than B? By actually helping them understand how those can map to beta distributions. And when I say people, you could do it with, have 10 participants who are like people in this class, okay, who know what a beta is. But have 10 participants who actually don't. And can we give them interactive explorers or tools that help them formalize their intuitions? Another question is, could we then find a way of weighting people's approaches? For example, sorry to call it by shirts, but yellow and green shirt versus black shirt, right? Yellow and green might say, you know what, black shirt, you know way more than I do about what emails people are going to respond to. So I'm going to give my estimates, but I want you to weight my success and failures 1/10 of black shirts. Like you might say, arm 1 is a beta. I think there's 8 successes, 2 failures. Arm A is going to be 5 and 5. And then Blackshirt says, well, I actually think arm 1 is 9 successes, 1 failure. Arm B is going to be, 2 successes, 8 failures. And you say, do not weight us equally. Weight his 10 times mine. Weight his his success rate 10 times mine. And now that's a way of combining expertise and novices. You have something to say, but we want to weight his more highly. Cool. So this is where we actually now do an adaptive experiment. We assign 50-50 using human judgment, like we just talked about, weighting red shirts and green shirts, yellow and green and black shirts, or using a statistical model. Then as we get data, we can actually evaluate. 50 people got A, 50 people got B, or maybe even smaller, with both quantitative and qualitative metrics. And then we might say, well, A has a 9% chance of being better than B. But then we don't stop there. This is what makes it constant experimenting. In the real world, we won't just stop there. We keep adding new ideas. And so over time, we can actually keep adapting probabilities. Does that make sense to everyone, how this approach lets us quantify our beliefs and keep adding new ideas on the fly?
This does sound like a assessment measure requires a lot of trust and effort on the behalf of users. I can also imagine that if I say I'm very confident about something, I can try to skew it in one way adversarially.
Fantastic. That's another paper. Is that a Chi paper? Is that a paper in your area? Fantastic. When we're gathering experts, so I'll say it as a question. In this paper, actually, let me try something on the fly. Title: Eliciting beliefs from people to get better decision making, even when some parties want to sway the vote. Abstract. In this paper, we investigate ways of gathering feedback from different people to try and come to a group consensus, such as which emails we'll send out at a company. We investigate policies ABC, which are ways of combining input from different people. And we investigate weighting schemes F and Y. And we show how if someone believes they're right and will use that to sway the majority, this scheme will suffer from bias in this way. To tackle that, we introduce this other approach. And that's a great one. That applies to everything. Going to lunch, deciding where we're going to have your retreat this year. And companies would love that kind of thing. There's a great term. Who knows what the hippo is? Ronico, you know hippo?
Is it a hippo?
Hippo. Highest paid person's opinion. Ronnie introduced this term and it's fantastic. How do most decisions get made? By the highest paid person's opinion. Don't trust the hippo. Your paper on this topic could be a way of getting input from people and trying to defend against the hippo swaying people's beliefs.
So, one thing that I haven't seen mentioned, but I'm wondering what your thoughts on it are. I actually do AP tests for all the papers that I write.
Amazing. We should write a paper on that for Chi.
Yeah.
All this stuff you all do, everything could be a Chi paper. If it's well done and rigorous, it could be. We just have to show it. Right? You will get rejection from Chi if you just write on your own, but we can show you how to make it a good Chi
The
paper.
rest of his comment, because I'm not sure. My question is,
Yes.
It wouldn't be very helpful to me to wait for humans to do the feedback on the AP test, because that would involve sending the papers, waiting for the feedback, sending the next paper. It's just really arduous. So then one thing I haven't heard you mention much is can you use the language model
LLMs,
AI
yes.
to help you quickly refine your prior, basically, because you can ask it to take on the role of a certain.
I'm trying to convince one of my grad students to work on that. I would love to write a paper on that. I think it's a quick, easy, highly impactful paper. Someone in your university, Rob Willer, has a paper on using LLMs to simulate human behavior. That would be a great paper to write. And I think there's 200 papers that can be on that topic in the next 10 years. Yes, let's do it. How? Let's talk about that after. Using LLMs to simulate human behavior is a fantastic idea to get priors, to do all of these things. Okay. So I think you all got a sense of basically some papers there. AV Scribe, Eustress, and you can read more about the others. I just want to dangle something in front of you so you're aware of this. Personalized and contextualized interventions, which I will not talk about too much today, but I want you all to be aware of. There's a lot of work by actually Ananya. So paper 2.1 is a small steps SMS. You could sign up for it now. It sends you messages every day to manage stress and be happier. and I just published a paper on design prompts that people reflect. So you can actually ask yourself questions to manage a stressful situation. So you yourself are personalizing and contextualizing advice to your scenario. He's got a nice paper in CSW on stories and messages. We give you stories about what other people are going through, whether it's handling stress or applying for an internship, and you're then able to actually abstract that away to your setting. This is a paper this year on how you can use an LLM, when LLM will actually work with you to figure out how to adapt a story that we've written to your context. And then a nice paper, 2.5, on how to use LLMs as a thought partner. So if you procrastinate, this will actually help you come up with messages to send yourself when you're procrastinating. And it has a particular prompt engineering and interface to get people to actually come up with better messages for the LLM. I'll put that one in front of you all. Actually, let me just entice you all. Okay, so just look at the screen, really careful, it's going fast. 2.1, 2.2. Next. 2.3, the messages. The result, example of a message. The results. 2.4, how do you contextualize a story with LLMs? You would share some context about what you're going through, and the LLM will actually generate a story for you from that. And then we actually found this. I was shocked. It actually outperformed just a human story. 2.5. LLMs is a thought partner. So here's the interface. You can just go to Tiny Spark paper or Spark demo, and you can actually type in what's going on with you, what you're procrastinating, grant deadlines, talking to someone, exercising. You type it in. You tell the LLM, tone, informal, direct. For me, do you want a Trinidadian response or do you want a North American response? Because I can tell you, Trinidadian family, friends, colleagues, and parents do not talk to you the same way North Americans talk to you. Much harsher. And then it will actually generate a message for you down here. You can actually edit the prompt to change your message. I want a really tough Trinidadian way of saying this. And you can also generate more messages. Does that make sense, people? Just at least as a teaser of what the interface could look like? And I want to say, all the stuff at OpenAI and so on are hiring, I think they're really missing the boat. And you all can eat them for lunch. It's the interfaces on LLMs that matter. This kind of interface is night and day. Don't just give people good LLMs. Tell them how to use it. Give them ways of interacting with the LLM. Tell them what to say. Give them custom prompts. Like this interface is kind of that makes all the world of a difference. Because you know what most business people are saying now? I haven't seen a case where AI really matters. Where's the business value? So their company's valued at 100 billion plus. Make some use cases like this that will actually show people where it's helping using psychology and HCI. That's going to matter. Okay, now here's back to adaptive experimentation, okay? And especially, I think Ronnie will be interested in this one. Okay, so what's going on in this graph? How can you use adaptive experiments to discover when the best intervention for a statistical minority is the opposite of what's best on average? So do you all see what's happening in this graph? You can choose your own setting, but I'll give you an example. This is what we won, part of what we won the X Prize for. Imagine students get messages, and the outcome of the reward is, do you generate a question? Are you going to generate a question about what you're learning in an online course? So how do we get you to generate more questions? Well, one self-focused message in blue might be, generate a question because it'll help you spot gaps in your knowledge. Another in red might be, generate a question so your peers might learn more from it. Now, if you look at this data set, right, you'd say, well, look at that. On average, the red message is giving you more people generating questions than the blue. But what's wrong with that? What are we missing? This is the data broken up by people who have lower accuracy because they got the last problem wrong. This is higher accuracy because they got the last problem right. And now, higher accuracy people are 80% of the data. 80% of people are getting the last problem right, so they're high accuracy. 20% get it wrong. And so what's actually happening? How is actually taking just the average, actually discriminating against a statistical minority? Can someone say that? Blue shirt and hoodie. How are we actually discriminating here?
Well, so since like 20% of the data, you have like more self-focused questions. Like, so if you only look at 20% and then 80% of the data given the other one, you combine them, like the weighting is far more towards the higher accuracy. So then like in the sort of overall results, that'll be reflected more because of that 0.8 versus 0.2.
Exactly. 20% of people, the blue message is better than red and substantially better. But for 80% of people, red is better than blue. So when you combine it, they get washed out. And so you would actually end up as a policy saying, let's give everyone red. And you'd actually be hurting people who are getting worse of it. And what's worse, you're hurting a statistical minority. Another question, do you think this is a bigger or smaller problem if you don't run experiments and you just use your intuitions or qualitative data? I think it's bigger. If after class today, I given 2 ways to explain a concept, and 3 of you came up and said, hey, I like the red way, I'd be like, yeah, I'll give red to everyone. But because I didn't keep experimenting, I would actually have missed the chance to discover there's a subset. And we're doing this constantly. Experiments are just a microcosm, a very well-defined one of what we're actually doing every day. So here's an example of how we would actually want to run this experiment, how we do when we use contextual bandits. So you assign 50-50, right? But actually, do it separately for the low accuracy and higher accuracy groups. So then what happens over time is, as we see what's working, we would actually start helping the higher accuracy group. There'd be a 70% chance that red is better than blue, and so they get 70% of the time. But we're not so sure for the low accuracy. We might keep it there 50-50, right? Like 55-45, we're not sure. And that not being sure is good because we collect more data. To me, actually would be like, oh yeah, there's an 8% chance that red is better than blue for higher accuracy. But for low accuracy, there's a 65-35. So do you all see how this approach would allow us to keep collecting data over time? We don't stop the experiment too early. We adapt it. So we might actually be able to discover what's better for a subgroup. Make sense, everyone? So I want to ask you all, what are scenarios where we decide option B is better than option A? Because it seems better for most people. But we might actually be hurting a minority. And I will say, when we use this algorithm, it doesn't just lead to better outcomes for people in a small group, like I think it was 20% better. It actually increases the statistical power to detect that effect. And you all see why, right? Because we keep experimenting. So we might start giving more people this in one group because we're pretty sure. But because we're less sure, we keep getting data. So we actually get higher power to detect this difference. We're more likely to figure out there actually is a difference. Oh yeah, here's the data. So the outcomes to the minority in a traditional experiment uniform random, 0.36. 0.36 of people generated a question, 36%. In adaptive experiments, 0.45. So that's substantially better. They get better learning outcomes. Statistical power to detect the best option of minority increased from 87% to 89. Doesn't look like a lot, but those add up. And I think in terms of sample, that might be 50 less samples. 50 less samples to be equally confident is pretty good. Even 5 less is good, right? Those are 5 people who didn't have to be in your experiment to get the same confidence. Good, so what do people take away from this so far? All right, now unfortunately, I did actually give you that whole first talk, but it looks like you all had a good time. But now I'm gonna give everyone a 1-minute break, and then I'm gonna actually talk about the algorithm work. New algorithms, new analyses. So everyone take a minute and think whatever you want to think. Ignore me up here. Let me give one thing away, this most important thing. 6 years ago, I thought and I ran experiments using Thompson sampling. Today, I would not tell someone to use that.
Would you say more? We spent a lot of time talking about it.
Fortunately, there's an easy solution.
Okay.
What is epsilon Thompson sampling? Epsilon of the time, do uniform random. Epsilon of the time, do 50-50 assignment, and then do Thompson sampling.
I see. So more exploration.
You could think of it as more exploration. I think about it in terms of this. Keep doing some amount of traditional experimentation in order to reduce the biases of Thompson sampling. It also guards against, one, if the world changes. Maybe explanation A is great, but then people get fed up of it. Maybe explanation A is great for your majority population, but actually there's a minority that you're missing. Maybe explanation is great for Stanford students this semester, but next semester it's not. So having some amount of epsilon uniform random, epsilon traditional experimentation is really important. And epsilon Thompson sampling says with probability epsilon, do uniform random. If epsilon is 0.1, 10% of the time you do uniform random. If it's 0.2, 20% of the time you do uniform random. Now, there's a second part of this. How do we actually now analyze data from Thompson sampling? A lot of papers will do all kinds of fancy debiasing stuff, inverse probability weighting, all kinds of things. I don't think these are working nearly as effective as people think they are. So one thing we've been developing, and I feel confident we can actually tell people you can actually use this, is an algorithm-induced test statistic. So what that means in a sentence, and I'll show you more, is when you do like a z-test for proportions, like is the proportion of people who, if you compare explanation A versus B and see who thumbs it up or not, you do a z-test to say, is there a significant difference between these? And so the z-test is designed for assumptions of uniform random. But you know you're using Thompson sampling, or ideally you're using epsilon Thompson sampling. So how do we actually now analyze the data in a way that takes that into account? That we were not collecting with uniform random, but epsilon Thompson sampling. The algorithm-induced test statistic basically takes the z-test statistic and it regenerates it using the algorithm to collect the data. So I'll show you more about that, but basically it generates the data under the null hypothesis using the algorithm you actually used, and it gets a different distribution for the test statistic, and you get a different cutoff value for doing your hypothesis test. Now, if you do that, it actually doesn't look too bad at all. You get a fixed false positive rate, whereas we've shown that even in a 2-arm trial, Thompson sampling will push your false positive rate to 13% compared to 5%. And your power actually is not bad. Uniform random gives you better power in a 2-arm trial. Thompson sampling gives you 46%, but epsilon Thompson sampling with this algorithm-induced test will give you 66%. Particular algorithm we used and developed, we think can do even better. So key takeaway here is, I actually would say now we have something that we can tell people. You're running an experiment adaptively, use epsilon Thompson sampling, or use our version, which is called TS positive, which is adaptive epsilon Thompson sampling, and then use the algorithm-induced test statistic that other people have developed and we've applied in this context and extended.
I want to make sure I understand. So you're saying that traditional Thompson sampling has a very specific trade-off between its false positive and other error type?
Yes.
But like, you can kind of mess around with the algorithm a bit and get other trade-offs that might be more practical for your study?
More statistically sensitive. Give you good inference. Yes.
Okay, so like
that's right.
It's like one is like Thompson sampling is like not even on the Pareto frontier necessarily. And then like if you change the algorithm a bit, like you can kind of get like better uniformly.
Yes. So thank you for being precise, and it's great you're echoing back. So one is that Thompson sampling has some issues and we've characterized how big they are. So I'll say that, yes. The second is that using epsilon Thompson sampling, or ideally adaptive epsilon Thompson sampling, which we're working on, will give you better statistically sensitive results. But the third is you also should modify the way you're doing your statistical tests. That's the algorithm-attuned analysis.
Okay.
So does this make sense? Just make sure people know what's happening. Just read that and see if it makes sense. This is the world we're living in, right? So think about there's an arm difference of 0, the probability P1, P2, 0.5 response rates to explanation A or B, or think of arm difference of 0.1. 0.45 of people will say they like explanation A, 0.55 explanation B. And this wall z-test is what you use to compare means. So you're basically subtracting the sample mean, portion of people who said they like explanation A from B, and then you get the standard error of the difference, which largely depends on the sample sizes, N1 and N2. Make sense, everyone? That's a very standard way of doing this analysis. Okay. Now, you can see this in the paper, but basically, here's how Thompson sampling actually inflates false positive rates compared to uniform random. We did a bunch of other tests, Welch's t-test, Bayes factors, all cause an issue. Inverse probability weighting also cause a problem. And then Thompson sampling induced wall test. So this is the algorithm-induced test. Controls false positive rate of 5%, but power is 17%, which is not great. How is the probability of detecting difference when it exists? False positive rate is there's no difference, but you think your test says there is. This is a sense of why this happens in Thompson sampling. I'll give you all 20 seconds on that. Basically, when there's a random low and a mean looks lower, you think there's a difference when there isn't actually. So that's where you get false positives, the high in Thompson sampling, why they're 13% of the time, not 5%. Because, actually, this is important, so I'll just go through it. So what you see on the vertical axis is the sample estimate of the mean, right? In reality, they're both 0.5, in reality. However, what happens is that if one looks worse by chance, right, arm P2, well, then actually stop sampling from it, right? And you put all your samples up here. So what happens in the limit? Even with 800 participants, you are accurately saying that arm 1 has a mean of 0.5. And the standard error is very tight. You're very confident, right? Most samples are there. But look, you think that actually arm 2 has a really low mean. You're not as confident, right? But you're still going to have a false positive because you put so many participants in one arm that you now think there's a difference. Does that make sense to everyone? That's one reason why. When there are random lows with an adaptive algorithm and something looks worse, you stop sampling. And so you start to believe that there is a difference because you put all your participants in one arm and you think there's a difference when there isn't. Great. This also explains why you get lower power. In a sentence, as Ronnie said in the chat, if you're saying uniform random, right, you're going to have like 400 people here, 400 people here. But actually, there is a difference, and you estimate the means accurately. But actually, you're not that confident because look how big the standard error is here. Problem is, you don't know, is there actually a difference or not? That's the problem we have in experiments. This also happens with Bayesian inference as well. Again, I'll let people look at this after they talk, but even when there's no difference in our means, the standard probability is going to be 0.8 or higher in 53% of the time. There's no difference in R means. The Thompson sampling will tell you that the probability of one R mean better being 80% or higher is really, really high. Okay, so how's the first part about empirically exploring, right? This is the empirical work we do.
But just the
Yes.
anchor on the previous comment, I guess. If you did epsilon greedy from the beginning, or just completely random,
Yes.
would that, I guess, I mean, fundamentally you're solving a stochastic optimization problem.
Yes.
That's a lot of noise. Would it be better in those examples?
Epsilon greedy is not better.
Okay.
Epsilon Thompson sampling, definitely.
That's better. It has better behavior for those, say, no difference settings.
It has a lower false positive rate and better power, exactly. But now here's what helps a lot, is this algorithm-attuned analyses, right? In a sentence, it allows you to control false positive rate to 5% instead of 13, but it also reduces power a lot. Yeah, I'm going to skip ahead a bit. But here's exactly what happens, okay? So this is the difference of 0, right? Here. This is difference of 0.1 here. Now, on the uniform random, this wall z-test is distributed like this. And this is hypothesis testing, right? What's the probability, if there's no difference, that you get a wall test statistic that's 1.96 or bigger, or minus 1.96 or smaller? What's the probability? The alpha is 0.5, 0.05 is 5%. You set the false positive rate. You say, I'm choosing 1.96. If my test statistic is bigger than that, reject the null. Just 5%. What's your power? Well, your power is basically, when there is an arm difference of 0.1, what's your probability that you get a test statistic bigger than 1.96? In this case, power is 80%, with a sample size of 785. Now, what does Thompson sampling do? For many reasons, but part of what I showed about how when it's lower, right, and you think it's worse, but it's not actually, it's basically giving you extreme values of the test statistic, really big values, because the arm differences are very separate. But that's actually not the reality. That's where you get 30%. But also, power is way lower, because again, it's reducing test statistic when there is a difference, because you actually don't put enough samples in that arm to tell. So do you see how Thompson sampling is actually reducing the signal from these two distributions? You can't tell apart when there's a difference versus when there's not. And so the algorithm-induced test does something very nice, which is it says, well, look, you've got the distribution on Thompson sampling. That's your algorithm-induced test statistic, right? So take the test statistic on the uniform random, generate it under Thompson sampling, and then say, well, let's set the cutoff values to be higher. Let's set the cutoff value to give you 5%. Make sense, everyone? And so now that's good. So you can actually just adjust from 1.96. In this case, it goes to 2.6. And now you've got a 5% false positive rate. But what's the problem? Problem is now, look at your power. It's 17%. That's because fundamentally, the data are not discriminating. What epsilon Thompson sampling or adaptive epsilon Thompson sampling does is it will drive those distributions apart. And so that's the takeaway I showed you before. Let me skip ahead. These are just some other results you can read later. Okay. So you actually need statistically sensitive algorithms. And this is the paper we're working on. I think it's may or may not be a quarter on that, depending where you're at. I think so. Okay. So here's the key idea, right? Let's investigate hybrid combinations of reward maximizing bands like Thompson sampling with traditional uniform random. So epsilon Thompson sampling has a fixed probability, but I'm going to quote an econ CS professor at Harvard, right? I don't think you want to be asking me about epsilons. If I come to you and ask you, give me an epsilon for the experiment, 0.1, 0.2, you can be like, Joseph, how am I supposed to know whether you do 10% or 20% uniform random? How is that my business? Aren't you supposed to be a statistician? You may know, but most people won't. So here's what we do instead, which I think is quite clever. One of the PhD students came with this idea. You can read about the paper there, okay? Okay. I'll give everyone 10 seconds to skim that. Now, you come, I tell you, like redshirt. What is a small difference to you? And redshirt might say, well, Joseph, 0.1 is small. If it's less than 0.1, then do tons of uniform random and get me good power and false positive rate. And so then we say, okay, well, here's what epsilon is. Epsilon is the probability that the difference between arms is less than 0.1. So if that posterior probability, that's why it's called TS positive. If the posterior probability of the arm difference being less than 0.1 is 80%, 8% uniform random. If the probability that arm difference is less than 0.1 is 5%, 5% uniform random. So do you see how we get a very nice epsilon of 80% or 5%, but something you define in terms of what's small to you? And of course, if the probability is low, we get more Thompson sampling. Does that make sense to everyone? This adaptive epsilon Thompson sampling, TS positive, says if the probability of the arm difference being smaller than the parameter you specify is x, then that x is epsilon. If the probability of the arm difference is less than 0.1, is 80%, then epsilon is 8%. If the probability of the arm difference is less than 0.1 is 5%, then epsilon is 5%, and that's how much uniform random we do. Make sense to everyone? And again, you can read the slides and so on. That's the algorithm there. It gives a nice trade-off across different sample sizes and different arm differences or effect sizes. On average, we do think it actually beats the existing algorithms because it adapts. Epsilon Thompson sampling will put 10% uniform random if it's big or small. Doesn't care. There's some more detailed breakdown, which I think is a nice way of breaking it up. But here's the kind of key thing, okay? When you use adaptive epsilon Thompson sampling, TS positive, it will actually better trade off reward, power, and false positive rates. And so now here's what I think I can finally say to people, okay? You're running experiments, then use TS positive and the algorithm induced test. Because then you will get a fixed false positive rate of 5%, not Thompson samplings, 13%, and even epsilon Thompson sampling inflates this. You get a fixed false positive rate, and your power will actually be pretty good. Uniform random is 87% power, Thompson sampling 46, epsilon Thompson sampling 66, but TS positive is 82. So now I think I can actually tell people, tell me what's the small difference for you, where you want to trade off reward and inference, and then actually we can use a good algorithm for that, and we can also give you a good algorithm-induced test. So that makes sense to people. This is just the first step in what I hope is 10 years of research. Well, not 10, 50, but I might not be around that long. I won't. Have more statistically sensitive algorithms, like Thompson sampling positive, which is an adaptive epsilon Thompson sampling, and use algorithm-attuned analyses, such as this algorithm-attuned test statistic, which will adjust the cutoffs based on the actual algorithm used. Great. So let me just review there. What do people take away from this? There's this vision of experimentation and coaching, We empirically explored challenges with the algorithms, give an example of an algorithm tuned test, and more statistically sensitive algorithms. And from the other talk, can think of your takeaways. But again, coaching behavior change, the approach of technology touchpoints being intelligent interventions through the adapcomp, give examples of adaptive experimentation tools like A/B Scribe and the Eustress positive stress, criticizing, contextualizing, and the future. This adaptive experimentation accelerates science and impact practice. Okay, so thanks so much, and just think about what you all took away from this.
Thank you.